Hi everyone, my name is Miranda and I'm going to be talking about the clapyron experiment. So the clapyron equation is going to be used to determine the relationships between temperature and pressure at equilibrium conditions in two different states. So we can use this to determine a couple different thermodynamic values. Most importantly, we're going to be able to look at the entropy of formation and the latent heat of vaporization. And that's going to be one of the main things that we're looking at during this experiment. So that latent heat of vaporization is going to be where the temperature line is constant, but there's going to be a state change from liquid to gas. So the objective of this experiment is to determine the latent heat of vaporization of water using the clapyron equation, and we're going to do this over a range of temperatures and pressures. And then we're going to compare the data using glass beads and without glass beads. So here is the experimental setup. So we've got the flask with the rubber stopper. This is where we're going to be able to kind of pressurize and depressurize, and where we're going to be holding that water. We have a hot plate to heat it up and to control the temperature. We're also going to have a thermocouple just to measure the temperature of the water during this process. We've got an analog pressure transducer to kind of keep track of that pressure, a mechanical pressure gauge, an air bleed valve just to make sure that we're in an okay range of pressure, a vacuum control valve, a centrifugal pump, a water reservoir, and a computer system with data acquisition so that we can keep track of all the things that we're doing. So right here you have a saturation pressure versus temperature diagram. This is created from the steam tables in the back of the book. I just took a range from 0 to about 250 to give you a nice image of what it should look like theoretically. So there's pretty much an exponential relationship between the temperature and pressure. So as you can see, as temperature increases, the saturation pressure should also increase at an increasing rate. So hopefully that's what we'll get when we do this. So this is the clapyron equation. So Psi is going to be the saturation pressure. T is the saturation temperature, or the working temperature, depending on what we're looking at. HFG is going to be the latent heat of vaporization, and VFG is the specific volume. And so this is the general clapyron equation. You can also use the ideal gas law to switch that equation around a little bit, make it a little bit easier to solve. So here we've got the change in saturation pressure over the change in temperature is a value of HFG times Psat over T squared times R, where R is the universal gas constant. And so using this equation and 3 different temperatures, I gave some kind of projected data. So if you look, we've got HFG from the steam tables on the right side, and then HFG calculated with the equation that you see at the top. And here the dP sat over dt, that's going to be the specific. I took the value of the saturation pressure before my the point that I was looking at, and I did the change in that over the change in temperature. And here you're going to have to, you need to make sure that your temperature is in Kelvin and that your pressure is in kilopascals. And then again, a caution, check the units of your gas constant R, because the first time I did this, I got some really wild numbers for my HFG, and then I realized that I was using moles instead of kilograms. That's a big difference. So yeah, just make sure that you use the right value. Overall, the experimental results using the equation seem to be pretty similar. For the first two, you can see it's a little bit lower than the steam tables, and then for the last one, it's a little bit higher. So that kind of suggests that we maybe have a little bit steeper of an exponential relationship to expect from these calculated values. And then here are my sources. Yes?
Can you get back a slide? So I was the group reporter for this project whenever we did it, and I was just curious in your thoughts because it concerned me, and we had the same problem where, unless I'm looking at it wrong. Yeah, so the HFG from the steam tables, as temperature increases, the HFG decreases, but the opposite is true for the calculated. And like, I was just curious in your thoughts of why that might happen, because like I said, we experienced the same problem. Any thoughts there? Because like the numbers are pretty close. Actually, your numbers are closer than mine, but your numbers are really, really close. So it's like makes it seem like it would be accurate, but the trend is different.
Well, this is still using data from the steam tables. Like this is using the pressure, the saturation pressure and the temperature from the steam table, so that would, I guess, make it more likely to stay kind of in the right area. I'm really not sure if there's a,
And I didn't come up with an answer either.
yeah, I really can't tell you. I'm not totally sure. I'll have to look into it a little bit more.
Okay.
What's the question?
So I was the group reporter for this clapyron experiment whenever we did it, and the HFG from the steam tables decrease as the temperature increases, right? So it's like 239, 230, 2258. But then the calculated, the opposite true. It doesn't decrease, it increases. And so that's what she has, and that's what I had too whenever I did the group reporter. And like I was just curious about why. I was just getting her thoughts on why that might happen, because I wasn't exactly sure. But I experienced that error. Because like the numbers are really close, but the trend is different, which is kind of concerning.
This could also be, that could be
I
because of
think it will be
the pressure.
saturation pressure that we obtained.
Because
There will be nothing to do with temperature. So it's
Okay.
either the saturation pressure that was obtained
Okay.
and how you completed the P, the T. That should be the reason.
Okay.
If the relationship between the P, the T that you're using is different from what is actually happening, then the plan should be different.
But if you look at this equation now, the change in pressure based off of this should be increasing with increasing temperature. So this value theoretically would be getting larger
Right.
as you go on. So I'm honestly
That's
not sure
true,
why
yeah.
the steam tables would have
Yeah,
a
that's a good.
decreasing relationship.
Well, the plot that you just showed doesn't match with steam table.
This is directly from the steam table. This is data from the steam table.
Okay, so now when you look at this plot, it's more or less like exponential. How did you compute the PDT?
Sure.
It was the difference in the saturation pressures
Yeah.
over the temperature
Yeah.
change.
So how did you compute it?
I just did, like P minus P over T minus T.
That's it. So
Well-
basically, from your value, what you just said now, P minus, let's say P2 minus P1 over T2 minus T1 is assuming a linear function.
Yeah.
Yeah, but you
So
do
that
that.
would be accurate if you have a linear function.
I'd have to relook at my work. I
Just
don't
like
remember we did
this
this.
one.
That's why they need to
The
do
slope of
different
the
ways.
exponential.
Yeah, I took the slope of like the tangent function to this.
Then stop.
Right, but you'd have to sum the slopes.